In this lesson, we're going to take a look at how parameterization works and how different parameterization methods affect the shape of the curve when we're creating curves using the breakpoint method. When we're working with breakpoints in the curve node, these parameterization options become available to us. If I switch the method to CVs for a moment, we see that those parameterization options are grayed out. When we're creating curves using the breakpoint method, the parameterization method that we choose can have a large impact on the shape of the curve. And also further down the track, they can have a big influence on the texture mapping of a surface that we might go on to create using this curve. The default parameterization method is uniform, but if I change this method from uniform to chord length, we see that it has an impact on how the curve interpolates between the different breakpoints. At the moment, we're not seeing a huge change because my breakpoints are fairly evenly distributed in 3D space. If I add a fifth breakpoint in this last segment of the curve here though, which I can do by making sure that my handle tool is active and then holding down the shift key, I can click on the curve to add a new breakpoint. Now, if I move this point close to this third point, we see that the curve starts to loop back on itself, even though I haven't actually crossed these breakpoints over to deliberately create a loop. So now we've got 2 points positioned closely together in 3D space. What we see when we're using uniform parameterization is that in parameter space, the knots are evenly, or in other words, uniformly spaced apart. And that's what uniform parameterization means. It means that regardless of where we position these knots in 3D space, in parameter space, they'll always be evenly distributed along the length of the curve. If I just turn off this normalized basis option, we can see that the size of the parameter space, or the size of the domain, goes from 0 to 4. And that's an aspect of how uniform parameterization works. It gives each knot in sequence a unique integer, or in other words, a whole number, starting at 0 at the beginning of the curve and adding 1 to the value of each knot along the curve. If I change the parameterization method from uniform to chord length, we see that this time it has a huge impact on the shape of the curve. We're no longer getting that looping back on itself that the curve was doing between these two closely positioned breakpoints that it was with the uniform parameterization. If we look at the parameter space, we see that the distribution of the knots in parameter space more accurately reflects their relative proximity to one another in 3D space. We also see that the default size of the parameter space with chord length parameterization goes from 0 to 1. And the parameter values, or the coordinates assigned to each breakpoint, has a value between 0 and 1 according to its position along this line. The actual knot values do have a much higher accuracy than I've shown here, but I've just rounded these down to 2 decimal places so that we don't have really long numbers which overlap each other in this example. If I change the parameterization method back to uniform again, we can see the interpolation of the curve between the breakpoints changes back to how it was before. And the knots are evenly spaced in parameter space again, and we can see those parameter values increasing 1 whole number per knot. Now, the overall size of the domain doesn't make any difference to the actual shape of the curve. All that matters in determining how the curves interpolated between the breakpoints is the relative distances between the knots in parameter space. So if I normalize the parameter space again, and normalizing is just the process of remapping values to fit within a 0 to 1 scale, we can see that it has no impact on the shape of the curve whatsoever. What's important to the overall shape of the curve is the fact that the knots are still evenly distributed across the length of the curve, and we can see here that they increase in 0.25 increments from one breakpoint to the next. I should just point out that in the last lesson I did exactly this and remapped the domain size to a 0 to 1 scale, just to make it easier to understand the U dimension as a percentage distance along the curve. For most modeling tasks, it doesn't matter what the scale of the domain is. We're typically working in that 0 to 1 range, even if the domain is technically larger or smaller. It's only when we get to texture mapping that this domain size makes a difference, and even then we can easily rescale it at any point. So with this example, we can begin to see and understand how the distribution of these knots along the curve in parameter space influences its overall shape. These 2 breakpoints here in 3D space are these 2 knots here in parameter space. And we can see that even though they're closely spaced together in 3D space, in parameter space, they're actually quite a long way apart from each other. So it's a bit like taking a piece of string and pinching it at these points, so here and here. and then moving those 2 points close together. That string between those points has to go somewhere, and so in 3D space we see it loop back round on itself. When I change the parameterization method back to chord length, we see that those 2 breakpoints, or knots, in parameter space are positioned at a similar relative distance apart to their distance apart in 3D space, and so the curve fits much more easily between those 2 points. Something that's important to note though is if I turn on the point and primitive hull display, and now I change the parameterization back to uniform, we see that it has a considerable effect on where Houdini automatically places the control points. With Nurbs curves, it's really the control vertices which are doing the majority of the shaping work, and working with breakpoints is really just an indirect way of positioning these control vertices. When we're working with breakpoints, the different parameterization methods have a large impact on the automatic positioning of the control vertices, and therefore they have a large influence on the shape of the curve. So parameterization refers to the way that the breakpoints, or the knots, are distributed along the curve in parameter space. The parameterization method determines how those knots are distributed, and the parameter is the resulting coordinate of each of those knots along the length of the curve.